In this video, we'll be seeing about Graham-Smith orthogonalization procedure. So here we'll be dealing with the orthogonalization and the normalization, where in orthogonalization the vectors are made orthogonal to each other, and in normalization the vectors are scaled to unit length. The Graham-Smith orthogonalization procedure, it is a method which is used in the linear applications or the linear algebra in order to transform a set of linearly independent vectors into a orthogonal or orthonormal set. Okay, so here we'll solve the linear equations, and this transformation, it is important because working with orthogonal vectors, it will simplify many mathematical operations such as projections, then decompositions and inner product calculations. And one of the main reasons for using the Graham-Smith is to construct an orthonormal basis for a given subspace. So an orthonormal basis it consists of vectors which are both orthogonal, that is mutually perpendicular, and of unit length, and such bases are specially useful in simplifying the vector calculations, then ensuring numerical stability and reducing computational complexity. So in practical applications, the Graham-Smith plays a critical role in QR decomposition of matrices, and these are widely used in the solving systems of linear equations and the least square problems, and it is also used in computer graphics, signal processing and data analysis. So here the orthonormal vectors produced by this method, they will help in preventing issues caused by the rounding errors in numerical computations. And the Graham-Smith, it is a foundational tool in linear algebra which will improve the accuracy and efficiency in various mathematical and engineering applications. This is the procedure, or you can say the steps in order to orthonormalize the vectors. The first step is to identify the vectors, that is, you have to recognize the set of linearly independent vectors to be orthonormalized. Second step is orthogonalize the first vector, that is, we have to ensure the first vector is orthogonal to the others by subtracting its projections. And next is normalizing the first vector, that is, we have to scale the first vector to unit length and make it orthonormal. So here next, these two steps are repeated for the other vectors, that is the remaining vectors. That is, we have to again orthogonalize the second vector, then normalize the second vector, and so on. We'll do it for all the remaining vectors. Now consider m number of real energy signal, that is in the time domain, okay, which are represented by S1 of t, comma S2 of t, S3 of t up to Sm of t. Because here we are considering m number of symbols, we are taking the symbols up to Sm of t. And here we'll consider n number of orthonormal basis function, which are represented by phi 1 of t, phi 2 of t, phi 3 of t up to phi n of t. Here we are taking n number of orthonormal functions. So the orthonormal functions are nothing but these are the set of the functions which is orthogonal as well as normalized. And here for a time interval a to b, we have two basis functions, that is phi I of t and phi j of t, and this should be equal to 0 when I is not equal to j, and it should be equal to 1 when I is equal to j. So here we have to these must be orthonormalized. These have to be perpendicular, that is orthogonal, and also these has to be normalized. Okay, so here it means that that is the orthogonal is basis functions are perpendicular to each other, and normalizes the magnitude, or these must be scaled to unit 1. And here we can write it as integration from a to b phi I square of t is equal to 1. Now here we'll take two basis functions, that is phi 1 of t and phi 2 of t, or you can say just simply as phi 1 and phi 2. So here we are taking three symbols, that is s1, s2 and s3, and there are two basis functions. Okay, always the number of basis functions should be less than or equal to the number of symbols, that is n should be less than or equal to m. Now here we are taking two basis functions, that is phi 1 of t and phi 2 of t. There are three signals s1, s2 and s3. So the number of basis function is 2, that is phi 1 and phi 2. So n must be always less than or equal to m. Now we will go for the first step, that is finding the first basis function, that is phi 1 of t. So phi 1 of t, it is given as s1 of t divided by square root of E1 of t. E1 of t is nothing but the energy of the first signal. So this can be written as s1 of t divided by square root of E1. Now from this equation we can write the value for s1 of t as phi 1 of t multiplied by square root of E1. Now here E1, that is square root of E1, it is nothing but the projection of S1. This is the projection of S1 on phi 1. Okay, that is nothing but your square root of E1, and that can be written as S11. Okay, that is the projection of S1 on phi 1. This is small s double 1 phi 1 of t. So S11 is what? It is the projection of this signal S1 on phi 1, and that is equal to square root of E1, because of which in place of square root of E1 we have written it as S11. So this capital S1 of t is S11 into phi 1 of t. Now next we have to go for step 2. Here one more thing is the energy E1. It is given as integration 0 to t s1 square of t dt, and here t is nothing but the bit duration. Now we have to find out the second basis function, that is phi 2 of t. So here S21 is nothing but the projection of signal 2 on phi 1 of t. So this is the signal phi S2, okay, that is this one. So here its projection on phi 1 is this one, here this point. So S21 is projection of signal 2 on phi 1 of t. Next we have S21 is 0 to integration from 0 to capital T S2 of t phi 1 of t dt. This is the value for this is the equation or value for S21. Now we have to define an intermediate function G2. So G2 of t is equal to capital S2 of t minus S21 into phi 1 of t. Now we need to find out the value for phi 1 of t. So phi 1 of t, sorry, we need to find out the value for phi 2 of t. So phi 2 of t is G2 of t divided by integration 0 to t G2 square of t dt. Now we have to substitute the value for G2 of t in this equation, okay, here in the numerator and the denominator. So we get G2 of t is S2 of t minus S21 phi 1 of t square root of integration 0 to t. What is G2 value? It is S2 of t minus S21 into phi 1 of t. Its square dt. Now we have to apply here a minus b whole square formula to the denominator. So here we get this numerator remains same. In the denominator, this is a and this is b. So first term will be a square. that is s2 square of t. So it will be 0 integration from 0 to t s2 square of t dt plus next this square, okay, second term square. So again integration 0 to capital T s2 1 square into phi 1 square of t dt. Then you have minus 2ab. So minus integration from 0 to t 2 into ab. What is a value? So here a is s2 of t into b is s21 into phi 1 of t. So you can rearrange and write it as 2 into s21 into s2 of t into phi 1 of t dt. Now next step is this numerator remains the same, whereas here 0 to t integration 0 to t s2 square of t dt, it is nothing but the energy of the signal 2. So you can write it as E2. Next you have here integration 0 to t phi 1 square of t dt, its value is 1. Okay, this term will take out of the integration, that is s2 1 square, and remaining term, that is integration 0 to capital T phi 1 square of t dt, that value is 1. So we get here s2 1 square. Then minus, so here again we'll take 2 out of the integration and s21 out of the integration. The remaining term is integration 0 to t, then you have s21 into phi 1 of t. Here here we will take s21 out of the integration. So the remaining term is what? The remaining term is s2 of t into phi 1 of t dt. So if you see here, integration 0 to capital T s2 of t phi 1 of t dt is s21. So 2 into s21 into s21, that will be 2 into s21 square. Okay, then we will get it as s2 of t minus s21 into phi 1 of t whole divided by square root of E2 as it is. Here 1 minus 2 is minus, so this will be s21 square. This is the value for phi 2 of t. Okay, then so this is what? This is nothing but our second orthonormal basis function. Now we have to check whether phi 2 of t is orthonormal to phi 1 of t. So for that what you have to do is we will take the energy of phi 2 of t. So energy of the phi 2 of t, it is given by the equation integration 0 to capital T phi 2 square of t dt. Now we will substitute the value of phi 2 of t, which is this one, okay, which we have obtained in the previous slide. So that will substitute here this value phi 2 of t. Okay, so already I have expanded this. So when you square this, the square root will be removed. So you will get here E2 minus S21 square. Okay, we have taken this outside, and in the bracket here we will apply the a minus b formula here, a minus b whole square formula. So we'll get s2 square of t plus here second term will be what? s2 square into phi 1 square of t. So you will get we'll take s21 square out of the integration, and in the integration phi 1 square of t remains minus 2 into s21, and in bracket remains s2 of t phi 1 of t dt. This is nothing but 2ab. Okay, so a is this one, that is s2 of t, and your b is s21 into phi 1 of t. So so here what we'll get? 1 minus E2 minus 1 divided by E2 minus S21 square as it is. Then this is nothing but the energy of the signal 2, that is E2. This is here, this value is 1. Okay, that is integration 0 to t phi 1 square of t is nothing but it is equal to 1. Therefore you get second term as S21 square, then minus S21. Okay, and this is nothing but S21. that is 0 to integration 0 to t s2 of t phi 1 of t dt is nothing but the value for s21. So s21 into s21, this is s21 and this value for this part of the term is s21. So it will be 2 times s21 square. Now after simplifying we'll get it as 1 divided by e2 minus s21 square into e2 as it is. So here 1 minus 2 is minus s21 square. Okay, here the numerator and the denominators are same, so these will get cancelled and you get the value as 1. Therefore here we can say that phi 2 is normalized and it has unit energy. Okay, now next for orthogonality, here we should get the value as 0. So for that, that is to check the orthogonality, we will use the equation integration 0 to t phi 1 of t into phi 2 of t dt, that is equal to, okay, so here we have substituted for phi 2 of t and phi 1 of t, we have kept it as it is. Fine. So this is phi 2 of t. Phi 2 of t is this, that is s2 of t minus s21 into phi 1 of t divided by square root of e2 minus s21 square. So again when you substitute here, this term, denominator term, will take this side outside the bracket, and inside the bracket what we have done is we have multiplied phi 1 of t with both these terms, that is s2 of t into phi 1 of t minus s21 into phi 1 of t into phi 1 of t, that is nothing but phi 1 square of t. I have not written here t, but t should come here, that is phi 1 square of t dt. Next, again this term will be as it is in the bracket. What you will get here, s21 will take out of this bracket, so you will out of this integration you will get 0 to t phi 1 of t dt. So 0 to t phi 1 of t dt is nothing but here will not take outside, that is the complete value for this first term is nothing but s21 as we have seen in the previous slide, and here this term, okay, here s21 will take outside the integration, and integration 0 to t phi 1 square of t dt is nothing but 1, that value is 1. Therefore here you get it as s21. Now s21 minus s21 is 0, so here the value will be 0. So when you get value as 0, here we can say that phi 1 of t and phi 2 of t both are orthogonal. So we got the first pair of orthonormal signal. Okay, that is phi 1 of t and phi 2 of t are nothing but orthonormal, as they are both orthogonal and even both are normalized. So next step 3 is finding the value of third basis function. So here we have to find the projection, that is S31, the projection of the signal 3 on phi 1, that is S31. So here you will get it as S31 is equal to integration 0 to t S3 of t phi 1 of t dt. Okay. Now here we need to find the second projection also, that is we need to find out S32 also. Okay, as this is our third signal and already we have two basis functions. So S32 will be given as integration 0 to t S3 of t phi 2 of t dt. Next we need to find out the intermediate function G3. So G3 of t, it is given as S3 of t minus S31 into phi 1 of t minus S32 into phi 2 of t. So here we'll take the minus sign common and in bracket remains S31 into phi 1 of t plus S32 into phi 2 of t. Okay. So here this one, that is sorry. Now we need to find out the value for phi 3 of t. Okay, phi 3 of t will be G3 of t divided by integration 0 to t g3 square of t dt. Okay, so again we need to substitute the value as we have substituted in the previous one while finding the when we got the intermediate of g2. Okay, that is g2 of t, we got the intermediate value. No, similarly here we have to substitute for g3 in this phi 3. Previously we have substituted the value for g2 in phi 2. Now we have to substitute the value of g3 into phi 3. So when you substitute here, you get this one. So this value we are substituting here. Here directly I have written the answer. So you can directly write the answer like this. So here you will get it as S31 of t phi 1 of t minus S32 phi 2 of t. Okay. And here it is divided by square root of, here you should not get t value. Okay, this t should not be there. You should get only this as S31 into phi 1 of t minus S32 into phi 2 of t divided by E3 minus S31 square minus S32 square. Okay, now we can write the general formula for the intermediate function gi of t as si of t minus summation j is equal to 1 to I minus 1 Sij phi j of t, and phi j this Sij value can be written as integration 0 to capital T Si of t phi j of t dt. So this is nothing but the value of the projection, and here I varies from 1, 2, 3 up to n. So this was about the Gram-Schmidt orthogonalization procedure. Thank you.